Good afternoon, everyone, in person and online. This is a hybrid seminar co-hosted by the Interdisciplinary Transportation Engineering Graduate Seminar, as well as the TBD Center at ASU. So today we have the pleasure to have Chuheng Wei, and he's a Ph.D. candidate in electrical and computer engineering at UC Riverside. His research focuses on vehicle-to-everything enabled cooperative driving systems with emphasis on cooperative perception under non-ideal sensing conditions and data-driven modeling for multi-agent interaction, trajectory prediction, as well as connected and personalized automated driving. Chuheng has co-authored over 20 peer-reviewed publications in leading venues across intelligent transportation systems, as well as computer vision. His work on V2X, cooperation perception method, has won the first place in the CVPR 2025 challenge and received a best paper nomination at IEEE. So if everything is good with everyone in person, with the audio setting and everything, and Chuheng, we can see your screen very, very, very well, and we can hear you as well. So if there's nothing further ado, we can just go ahead and get started. Welcome, Chuheng.
Hi, hi, Amy. Thanks for introducing. It's my great honor to show my project today to your guys at ASU. First of all, let me have a quick introduce about myself. I'm Chuheng Wei, a PhD candidate at ECE department at Riverside, and I will start to be a postdoctoral researcher next month at Purdue University. My background is about a smart connected vehicle. I finished that at University of Warwick, UK. Before that, I finished the digital media technology bachelor degree at Communication of China. I also have some experience. For example, I used to be applied scientist at Amazon and a research intern at Osme about to do some computer vision based method. My research direction mainly focus on the cooperative perception, computer vision, as well as some sensor fusion and personalized driving behavior. Today, I will mainly talk about something about cooperative perception, V2X, as well as some personalized driving behavior. Uh, First of all, let me have some introduce about my talk. My talk will mainly have four parts. The first one is the motivation and background. Then I will introduce three parts of my research: the cooperative perception, cooperative prediction, as well as some personalized autonomous driving. So let's start with that. So to start, I'd like to briefly talk about how autonomous driving is evolving. Traditional, most autonomous driving systems rely heavily on onboard intelligence, meaning that each vehicle makes decisions based only on its own sensor or its own CPU or GPU. But this setup is fundamentally limited because the vehicle can only perceive what is its own field of view and make some decision by itself. Now, with the development of V2X communication and hardware and even some smart infrastructure or smart unit, we are moving towards a connected driving world where vehicle can communicate with each other vehicles and some roadside unit or even the cloud. This shift enable a much more collaborative perception and cooperative decision-making progress, where information is shared across this intelligent system rather than being installed within a single vehicle or a single unit. So instead of each vehicle operating independently, we now have a system where vehicle and infrastructure jointly contribute to safer and more intelligent driving system. We call it V2X system. And so after introducing what is connected vehicle, the first key point or the first key component is that perception. Perception is still the foundation of autonomous driving. Everything starts from the perception. Vehicles need to understand the world, the environment before they can predict or make some decision by their own or by the other unit. That include the perception include not only the objective detection, but also some position estimation of surrounding vehicles and the surrounding agent. However, different sensors have their own strengths and limits. If one vehicle only equipped with a camera, maybe in some dark scenario or some rainy scenario, the performance may be not good enough. But the camera can give us a lot of information about the color. So that's for camera, and maybe the other for LiDAR and for radar, they all have their strengths and limitation. For example, the cost may be very high, and the size is maybe very big. It's not suitable for each vehicle. So because of this limitation of the sensors, relying on a single vehicle with single type of sensors is not enough for the real world. A single vehicle's perception is fundamentally has its own field of view and the line of sight. It cannot see behind, obstructed or beyond the scanning range. This become even worse under some adverse condition as I show in the second picture. But maybe if we have some roadside unit, roadside sensors, or we can get some information from the other vehicles, it may help the Eagle vehicle to uh, have better understanding of the surroundings work. By sharing this information or the detection result between vehicles and the infrastructure, the cooperative reception allow us to expand the coverage of the vehicle and give the vehicle or the roadside unit a more safer world. So we finished the introduction about the perception, but even we solve the perception, that is not enough. Perception only tell us what is happening now, but autonomous driving also requires understanding what will happen next or in the following seconds. That is where precision comes in. Precision focuses on modeling future behaviors such as whether a vehicle will stop or turn or whether a pedestrian will go across the road. It also need consider interaction between multiple agents, not only through the vehicles, but also the vehicles to the pedestrian or the other VRUs. So the cooperative system need to be go beyond perception and incorporative filter interaction understanding for the prediction part. And this become especially important in complex scenario, as I mentioned in these slides, such as some singularized intersections, such as some ramp merging, especially in the highway or the dilemma zone, what I will mainly talk today. So the vehicle's trajectory depends not only on itself, but also on the surrounding vehicles and the traffic signals and the surrounding traffic scenarios. So instead of predict each vehicle independently, we need to model interaction jointly to build a wonderful prediction model. Then next step, most exciting prediction models still assume a generalized behaving pattern. They try to use one model uh, that fits all of the driver or all of the cars. But in real world, different drivers behave very different, even in the exact same scenario. For example, like the traffic light, when the traffic light turn to yellow, even the driver have the same distance or same speed to the traffic light or the stop sign. Some driver maybe decide to stop, and the others maybe just go straight and go across the intersection. So we cannot ignore the driver's behavior or the personalized driver behavior when we try to develop some prediction method. So this leads to the fatal motivation. We need to personalization and the driver behavior influenced by many human factors. But when we try to do this, try to develop some models on the prediction or the personalized prediction, we notice there is no data set focused on the person itself. We also found some data set that may be collected the data connected the driving data from different person with their own car. But the issue is that the car's size and the car speed, the car's characteristics will affect what will happen to the driver. And in addition, some condition also affect the driver. For example, I go this way to my home, but my friend maybe to use a highway to go home. So uh, their their traffic scenario are also quite different. So what we want to do is try to develop some not only some method but also to collect some data set. So first of all, I will introduce what is cooperative perception and what we did. Uh, the key idea for V2X cooperative perception is to extend the perception range beyond line of sight by sharing information between vehicles and the infrastructure. However, when we try to do some research, we found most of the existing model assume that all nodes have the same setup. For example, all vehicle use a camera and LiDAR. But in the real world, if we want to develop the cooperative perception, we cannot assume all vehicles have the same setup. For example, the vehicle in red, one of them have the V2X system, and the other also have the V2X system. But one equipped with LiDAR, for example, the Toyota or some other company, and the other only equipped with cameras, such as the Tesla. How can they share their information together? Since in our most of the researcher, they collected their data set by their own. They set up all of the sensors and the equipment by their own. They purchase it from the same website or the same company. So they are quite the same. But what we want to do is that we want to target the challenge scenario. We hope that we hope to do a cooperative perception model that can solve heterogeneous sensor configuration. For example, one vehicle only have camera, the other have camera and LiDAR, and maybe one have camera and the other have LiDAR, something like that. We totally found we totally found nine configuration for the V2X system and only consider the camera and LiDAR. We hope to develop one heterogeneous sensor cooperative perception system. Here I show the HycoFuse, which means heterogeneous cooperative perception fusion method for V2X system. The key idea is to design a system that can work across all possible sensor configuration without requiring some separate model. We hope use the same model to solve all of these things. I only show some brief part. For example, we use a BV fusion to do the single node or single vehicles fusion, and for the other part, we develop uh some attention method to do the cross node fusion. And in this image, we only show one scenario, which means the roadside have the LiDAR and the camera has the camera and the LiDAR information together. But we can solve all of the configuration from the sensor setup. First of all, let me introduce the single node fusion. For node that have multiple sensors, as I show in this figure, we use standard BEV fusion method to combine the camera's information and LiDAR's information together as here. But what if the node only have one camera or several camera or one LiDAR information? To address this, we introduced the pseudo fusion, which allowed a single sensor node to generate a wonderful feature or a whole feature for cooperative fusion. With this method, we can solve all of the feature fusion part. And here's for single node fusion. And we also need to finish the cross node fusion from two different nodes of the V2X system. On the one hand, we try to build the HAF part. The HAF part is mainly focused on, for example, the vehicle only have the camera information, but the roadside have the LiDAR and several camera information. We can use the China weight to balance that. We let the deep neural network to learn the weight by itself. Then we built the HAF. It depends on the performance or the setup of different node. So this HAF is a attention fusion. And additionally, we found if the camera only have maybe about 400 resolution and the LiDAR has a wide resolution, we also found it's a big issue or a big problem for this system. So on the other hand, we also do some adaptive spatial resolution strategy to try to do some downsampling and upsampling to resolve these resolution issues. These are the two key ideas. One is from the single node fusion, and the other is the cross node fusion. Then we evaluate the model under full sensor configuration in both daytime and nighttime, as well as the other sensor configuration. But for these two images or these figures, we decide to use the full configuration setup to do these two things. One is in the daytime and the other is in the nighttime. As you can see, the model maintains robust detection performance across different lighting condition. And then we can try to move to the qualitative analysis. As we mentioned, this method performs very great with the full sensor configuration, but this method achieved the first place in last year's CVPR V2X challenge. The interesting thing is the best performance method will not rely on the full sensor configuration. It's rely on the mixed configuration, which means the vehicle only have one LiDAR, and the infrastructure we use the LiDAR and cameras information. This method or this strategy reached the first place for the CVPR challenge. It is very interesting. When we have a discussion and try to visualize the result, we found this may be due to the issue with the dataset itself, which in the dataset mainly focus on one intersection where the vehicle are very close to each other, but the camera may only the camera can only detect one vehicle, which is the front vehicle with a camera. But if the vehicle set up with one LiDAR, the range will be maybe very huge. So it is why we have one LiDAR, the performance is better. If we have the LiDAR and the camera together, maybe the camera can only detect one front vehicle. So maybe the performance may be not good since the camera gives some negative influence to the whole system. So that's why we assume that the LiDAR and the LiDAR and the cameras configuration can reach the first place in the CVPR challenge. And this is one method or a project about the cooperative perception. Then next step, I will introduce something about cooperative integration modeling. Uh, Here, the focus is the prediction, trajectory prediction in the intersection. In the traditional trajectory prediction method development. Most of them are target the pedestrian. And even some method try to do some research on the vehicle trajectory prediction, but they all focus on some scenario without traffic light. They focus on the freeway or some intersection without the stop sign. But when we try to develop some method at some uh, complex scenarios, such as the signalized intersection, we found that many existing models do not consider the influence of the traffic light, even though they play a critical role in vehicle behavior. We think the traffic light is very useful in predict the behavior of vehicles at some signalized intersection. To address this, we propose the Kia GAN, which integrate traffic signal information and introduce a new attention-based polling mechanism to better modeling interaction at the signalized intersection. In the traditional method, they only use the position of each vehicle or if agent, then finally generate the trajectory. But in our method, we not only encode the position, but also some vehicle speed or accelerate and the type of the vehicle, since we found that when we consider the interaction between the vehicles, we found the vehicle speed or the vehicle size. For example, I drive a bus and the other guys drive a truck. It will affect the other vehicles a lot. So we not only use the position, but also use some motion parts such as the speed and also some physical information such as the type and size of the vehicle. On the other hand, we try to encode the traffic light information to the whole framework. Then when we do this research and finally get some good result, but we noticed that we consider these so much things, we also ignore part of them. For example, we ignore the intersection itself. We do not put any information about the map to the model. On the other hand, we only consider the vehicles at the intersection, but the pedestrian or the VRU impact a lot in the vehicles interaction. For example, if I found a pedestrian that want to go through the road, maybe I need to stop or something like that. So based on that, we improve our method. We named as enhance KIGAN, the EKIGAN. As I mentioned, we use the position, the speed, as well as the size. On the other hand, we also try to integrate the map information and the pedestrian information to the whole framework to try to get better performance. And here I show some result when we consider firstly take a look at the quantitative result. We found the Kiagan and the Ikigan get very better performance in this data set. The SIND data set collected in intersection in China. In this dataset, our method achieved the SOTA. And here I show some visualization result. In this method, we try to observe for 6 seconds and predict for the following 6 seconds or 9 seconds. And for each second, we have two frames. And the right part means the ground truth for the whole trajectory, not only include the observed, but also include the predicted. And for the green trajectory, it's the predict part. For example, we use the 6 second, then predicted follow 6 second or predicted follow 9 second. Uh, Here we can find maybe at the end point they are about the same point. So it means our method can get better performance in this data set. Even maybe some other method have a very close matrix with us, but our method also have some useful or some SOTA result. Here, I also try to do some ablation study. We found that our encoding part is all useful for this prediction result, especially the traffic light. And I not mentioned, we also try to develop some polling net to model the behavior or the interaction from different vehicles or different surrounding agent behavior. And these are the two cooperative part. One is cooperative perception, and the other is cooperative prediction. But when we try to do the prediction, we consider the speed, we consider the size, we consider the position of each vehicle. But we ignore very important part is the personalized. For example, I'm very angry. I will not perform very great at some intersection. I will directly go through the intersection even if it's red. So sometimes we also need to consider the personalized autonomous driving behavior in the prediction part. So the key issue in the existing trajectory prediction dataset is, as I mentioned, they ignore the role of the drivers, and the most dataset mix traffic behavior with other factor. So our uh, when we try to develop this method, we want to truly understand the driver's specific behavior. We need a controlled environment where variable like vehicle and road are kept the same. So to address this, we decided to connect the dataset and process the dataset by ourselves. We called it PDB, which means personalized driving behavior dataset. Here I will show some information about the dataset. Here's the overview of the PDB. We collect both the vehicle and the environmental data, such as for the environment, we collect the LiDAR information, the camera information, as well as the GPS information, and we also get some HD map of the whole road. On the other hand, we also collect some information from the driver, which is our focused part. We ask multiple drivers driving the same road. We collected the internal camera images, and we also use some uh, watch to collect the heart rate. And in addition, we also try to collect some CAN bus information. We monitor the pedals information and the pedals behavior as well as the wheel steering information. Uh, Sorry. On the right side, it is some processed GIF images. We do after we collected that, we process it to some trajectory prediction data set. And here I show some hardware setup. The vehicle is from Toyota, and we set up some camera as I mentioned, and we use OBD to collect some CAN bus. We use U-blocks to collect the GPS and one LiDAR to collect the surrounding world in a very high height. On the other hand, we also use the Apple Watch to collect some information, especially the heart rate of the driver itself. Here shows some high resolution result. We collect 128 line LiDAR and high quality camera images to capture detailed environment information. At the same site, as I mentioned, we also include an in-cabin camera to monitor the driver itself, to monitor the driver behavior and whether the driver is happy or whether the driver is very angry or something like that. So beyond the perception data, we also collect some additional modality. For example, we use the GPS to track the vehicle's position, and we use the CAN bus data to capture the vehicle's dynamics, such as the speed or whether stop. More important, we also collect the heart rate signal. We think the heart rate signal will provide some insight about the driver's physical status. By combining these signals together, we can better understand how driving state related to driving behavior. For example, in this image, we found the driver reach high heart rate at this corner. I will discuss that in next slide. In this data set, we will not only use it as a trajectory prediction data set, but also we also found some use case for this. For example, these three images are the road collected by three different driver. I show the detailed information about the driver here. Two interesting thing is that at this corner, since the first driver is a third year PhD student, he is quite familiar with all of the road at UC Riverside campus. So at this corner, his heart rate may be not very high, but for the others, the heart rate we can find great change. And another thing is that when we only consider the heart rate, we found the second driver's heart rate may be not very high. It is because the second driver maybe have more than 10 full marathon experience, so his heart rate may be not very high when he drive the cars. And here is the first potential usage for our data set. We hope somebody can use this information to do some uh, traffic or some personalized behavior analysis in some whole road. On the other hand, we also try to do some interesting research. We only use some VLM based method. We only use the driver's physical information, such as the uh, facial images, the heart rate, and some textual description of the driver. We do not use any information about the vehicle. We do not use any information about the surrounding world to predict the following behavior, whether the driver will speed up or whether the driver will turn left to right. We try to only use the driver itself information to predict that, and the result is also very interesting, very good. Even we do not use the environment information, we only use this personal information. It can also have a better performance. Since the paper has not been published, I do not show too much result here. And when we try to, after finish the data collection, we noticed that in the previous route or the previous data collection process, we can only collect the uh, driver's behavior in a road, but there are not too much standard scenario related to the personalized modeling. So we found one very interesting scenario, which is the yellow light dilemma zone. When we found a yellow light, when we found the light turn from green to yellow, maybe when we very close to the line, we may decide to just go through that. And if we found the light turning very far from the stop sign, maybe we most of us will just decide to stop. But there's also one dilemma zone. In the dilemma zone, some people maybe decide to go and the others maybe decide to stop. We found this situation or this scenario is very useful for our personalized behavior modeling. So we try to directly collect some data in this scenario. To study this problem, we first collected the data in a simulator environment. We use the color platform to simulate dilemma zone scenario and record the driver's response to the yellow light. We collect the distance to the stop sign. We collect the speed when they decide to stop. We also collect the decision time, and the most important part is whether the driver will decide to stop or go. We collect all of this information in the simulator. On the other hand, we also try to find one road. In this road, we found one stop line, and we equipped one traffic light in Canby to also collect some real-world data. We include the GPS trajectory, the decision, the traffic light timing, and we also collected some heart rate that I mentioned. Since we use the same vehicle and the same setup, we also try to collect some heart rate when they do the decision. By combining both the simulation and the real-world data, we can study driver behavior under different conditions and improve the generalization for each driver. Here is the method itself. We named the method as VISA-DZ, which means visual segmentic trajectory adaptation for personalized dilemma zone prediction. Uh, Here we use, first of all, we use the driver's historical trajectory site to do some visualization in the speed and the distance to the stop sign, as well as some stop and go. We collect all of this information and try to do some visualization. We plot all of this information. Then we use the VLM method to try to describe the driver's behavior. Use a plot to describe the driver's behavior. Then we use the description to describe the driver's behavior. Then after an encoder, we finally get the feature from the driver itself. And for each trajectory sample, we use three backbone. One is to precise the distance to the stop sign. One is to precise the vehicle speed, and another one is to precise the acceleration. Finally, we also get another feature. Then we have one feature from the driver historical information and one feature for the driver for the observed driver information, the trajectory information. Then we use some fusion method to fuse them together. Finally, we use a prediction layer to not only predict the stop or go behavior, but also the decision time. And finally, we can find some result on that since the paper do not publish yet. So I will not show some detailed information, but I can show the result. In this result, we found that for the fusion method, the FILM performs best in simulation, and the statistical feature failed to generating the real world data, as we can see here. And we also found the VLM-based method to describe the personalized behavior for the driver can enhance the prediction for the dilemma zone behavior prediction. So we think with this data set of the personalized driving behavior and this driver specific modeling, we can get better performance in futures trajectory prediction or the driver behavior prediction. So we think the personalized is very important. And this is all my slides today. Thanks for listening. If you have any question, please let me know.
Thank you so much, Chuheng, for your great presentation. We will take some minutes to collect the questions. If there's any questions in person or online, feel free to unmute yourself if you're online to speak directly.
Any questions from the room?
I do have one, if I may. I was just curious in the Vista DZ framework, since you were measuring like through the camera, like inside, and also the Apple Watch, right? I was just curious if you can comment, how is the prediction or use of this framework when the scenarios won't have this privacy related type of data collecting on the driver?
Sorry, for the Vista DZ, we do not collect some information from the of the face from the driver. As I mentioned, when we collected that in the
I see.
simulator, we do not have the facial information. And so on this data set, we also do not collect the facial information. Since it is quite different with the previous one, we also need to stop at this scenario, and the in-cabin camera maybe move a lot. So we remove this part when we develop the Visa DZ. But we also try to use some heart rate information. We try to do that in this framework, but we notice since we collect the data in Apple Watch, and the Apple Watch can only collect the heart rate maybe 10 seconds. So it's not real time. So the heart rate information is not very useful for our model. But maybe we can do some analysis for the driver's behavior at the dilemma zone. But we do not integrate that part in our model since the heart rate maybe collect 10 seconds, but we do the decision in 3 seconds. So the heart rate maybe not change immediately. So we ignore the heart rate part.
Gotcha. Thank you.
Okay.
And then for the fusion, data fusion, is the scenario only between the vehicle and the infrastructure? I guess if I were to more directly ask my question is, if could the data fusion be applied between the different automated vehicles, and if so, what would be the baseline requirements to for the data transfer? Because if you have a different company, how do you fuse data or in your requirements of that data fusion between two vehicles from two different companies, which will have their own handling, proprietary, and all that stuff?
Yes, since for our project, we do not consider different company setup. We only consider different sensor setup. And in addition, we also try to, here is what we did. And what we are doing is we try to change the position of the vehicle and change the position of the sensor. And we also try to change the size of the camera. For example, one vehicle only equipped with one camera, and the other vehicle equipped with several camera, and maybe one camera with high resolution and the others with less resolution. It is what we are doing now. We try to develop some method based on that, but we are still working on that. Since, as you mentioned, the data collected by different company, they are not very same. But we try to develop some framework that can affect this research area, not to do some real world setup or some real world solution. We just want to give an idea to all of the researchers is that we are doing that. Maybe in the future, your company or your partner can do it as well. Yes, that is what we did.
I see. Thank you. And really nice work. I don't see any more questions from the room. So Yanbing, I'll pass to you.
Yeah, sure. I do have one question. So, people in the audience, feel free to raise your hand if you do have other. So, if I understand correctly, your the personalization part was to collect personalized information on the heart rate and on the facial expression, etc., in order to understand or predict their behavior, right? And if that's true, I was just curious in one of the experiment that you had before on collecting the heart rate and drive the course of the campus. How much do you think that information helps to predict the behavior of the driver versus just to really understand, based based on their physique. Um, yeah, I guess I don't really quite understand the goal of doing this collecting personalized data.
Yes, since what we want to collect the personalized data is that uh, we notice a lot of people, maybe for example, if I drive a car, especially a autonomous driving car, maybe the stop decision are quite different for me. So what we want to do is to develop some personalized ADAS system. As you develop the personalized ACC, we also try to build some personalized autonomous driving system for different person. So we think the personalized information is very useful. So for this project, we ask a different person to drive the same car in the same road. And on the other, we found if we want to focus on the person itself, we also need to collect some data about the person. So that's why we try to collect some face information, the driver behavior information, as well as some heart rate information. We try to collect some information about the person itself. Then we notice that we have some information about the driver itself. What we want to do is that we develop the whole method of the trajectory prediction. One good try is that we only use the information of the driver itself to test whether we can use the driver information to directly predict their following behavior with the heart rate and the driver's face information. We notice if we want to turn right or turn left, our head maybe move a little bit. So maybe use this information, we can predict the following part. But for some autonomous driving vehicle, no vehicle or no car will only equipped with some in-cabin sensors. They will always have the external sensors. But what we want to do is we just want to try if we can only collect some behavior information from the driver itself, whether it can affect the or whether we can only use this information to predict the following things like that.
Mm,
Yes, it's just a
thank you
try.
very
I
much.
mean,
Yeah,
we cannot use
sounds
it
good.
in robot. Yeah.
I guess just to follow up on that, then, how do you have a verification method in place in terms of now you have correctly predicted that this particular behavior is tailored to this driver based on their personalized data? How do you quantify, I guess, the prediction is personalized enough?
Since we develop different model or different weight for different person and try to predict their following thing. One interesting thing is that we mix all of the driver together. We do not have any personalized information. We do not give the driver any ID information of that. We merge all of the information together to predict their behavior. The accuracy may be only about 50%. Since the baseline is 30%, since we only have three options: turn left, straight, and turn right. So, and when we try to predict, we mix all of the driver together. The accuracy may be only about 50%. But on the other hand, we try to give the driver some ID information as well as some description information. The accuracy can reach maybe more than 70%. Yeah,
Mm,
but for this, we only consider whether they will speed up or whether they will accelerate or stop. But for the other, we cannot estimate the exact speed or exact angle for the turning. We can only estimate some basic information for that.
thank you very much.
Thank
I guess one last question on my side, and I'll turn to the audience, is what do you like now you've the whole presentation was very comprehensive, right? You've done prediction, you've done modeling and personalization. What do you think is the most challenging part in the course of study? And also, how do you foresee that you carry this part of your study into the future?
Yes, the most challenging part for our research is that it's the data set itself. Since when we try to do some research, for example, the signalized intersection action, we do not have too much data set. We need to collect some data. Maybe the data is from China and it is not suitable for United States environment. So we need to collect the data by ourselves and try to do some data process by ourselves. And we notice it's very challenged. So we ignore that part. We only use China's data set, but we spend a lot of time to collect the data set. And when we set up to collect the PDB data set, we spend nearly 2 years to build up all of the data collection setup. For example, we purchase a lot of hardware, we purchase a lot of sensors, but we try to do the data collection. We found the time synchronization is very hard, and the data storage is also very hard since we need to collect a lot of data at the same time. The space or the ability of the network is also very important. So my suggestion to the others is that try to solve some problem when we found that. You just need to do that when you found some problem. You just try to solve that and check what is the next step. Since it is very hard to collect the data, but if you found the gap, you decide to do that, just go straight and do that. And no matter how long it will take and how many challenge you will meet, just do it. Yes.
That's well said.
Yeah.
Thank you very much. No, I also really appreciate that effort that you put into collecting this new data set. Great work on that.
Thanks so much.
Any other questions from the audience?
We're all set. Thank you.
Hey, great. All right, if not, Chuheng, do you have any last thing that you want to say to the audience before?
No, that's all my presentation today.
Sounds good. All right, thank you so much, Chuheng, for your great work and your presentation today. And then thank you everyone for joining and hope you have a great rest of your day.
Thanks so much. Have a nice one.
Thank
Thank you.
you.
Bye.
Goodbye.